I find the consent to being live streamed an interesting choice. That you're already consenting to be seen by everybody on Zoom. I guess you get the names of the people this way.
Okay, I think we're ready to get started. So hello everyone, my name is Jordan Alwan. Welcome back to the second lecture in the Distinguished Theme Seminar Series on Causal Inference. Before we get started, if you are watching on Zoom, we ask that you mute your microphone at all times unless you're asking a question. If you're on YouTube, you can write your question in the chat and we'll forward it to the speaker. For any students from Stat 692, make sure you sign in either on the sign-in sheet or log in on Zoom. And today we're honored to have Professor Donald Rubin visiting us. Professor Rubin is an emeritus professor of statistics at Harvard, where he chaired the department for 13 years. And he currently holds positions at Tsinghua University and Temple University. Professor Rubin has authored or co-authored nearly 500 publications, including 10 books, and he's one of the most cited authors in the world with over 340,000 citations. Professor Rubin is most well known for the Rubin causal model, a set of methods for performing causal inference on observational data, as well as for his work on analyzing missing data. Before we begin our seminar, Professor Dennis Lin will present the Ghosh Award.
This is in honor of our colleague, J.P. Ghosh, the family of Ghosh Award. Let me present that to Professor. And you take a picture there. Okay, now, just make sure you are done Rubin.
That's right. Who are you? I recognized him with the mask, but without the mask.
Okay.
Thank you very much.
So today, Professor Rubin will be talking about essential concepts for causal inference and randomized experiments and observational studies. And let's all give Professor Rubin our undivided attention.
Thanks very much. And I can't stand this thing, so I guess what I'm supposed to do is to protect all of you from my diseases, is to talk behind it. This work? Okay. I guess I have, what, about 50 minutes or 45 minutes, something like that, to talk. And I like to talk, but I don't like to give formal lectures very much. So this will, I tend to sort of ramble. And so this talk will have, do I have a
Pointer?
I don't care about a pointer, but a click, go forward and back, or do I use this?
You can use probably the arrow keys, maybe.
The arrow keys, okay, fine.
Yep.
Okay.
Oh, Tim has one.
Okay,
Forward and back should work.
okay.
And there's also a laser you can do it.
Gonna check if that works.
Yeah.
Perfect. Thank you, sir.
Great.
Can they hear him online if he's standing that far away?
Can someone online write in the chat if you can hear?
You have ceiling mics, or is
It's
this?
that mic. We tested with Doug yesterday.
Yes, we can hear in chat or on Zoom.
So, can people hear me?
Yeah.
No? Okay, good. So just some introductory comments about the title. What I mean by essential is really sort of in the mathematical sense of essential. I guess this is not something to lean on. End up on the floor. But I mean by essential is the mathematical sense of essential. You don't add stuff when you're trying to express something that's not needed. So essentially concepts that are central to the idea of causal inference. And in some sense, what I may be doing is, as the initial lecture in this series, is I don't mean this in an insulting way, but I think that what you'll be hearing in the other talks is what I regard as clutter. I mean, stuff that's not really needed. to understand causal inference. So it's sort of extra stuff that's not really needed, but is makes points about the presenter's perspective. And so for example, if you talking about a Pythagorean theorem, triangles, and you say that if you have an isosceles right triangle, the square of twice the square of the short sides equals the square of the longer side. Well, that's true, but it's got clutter in it. It's got something that's not needed to express the essential idea. So that's what I mean by essential. And the other part of a remarkable history, as I'll develop in the talk as it goes along. Why is it remarkable? Well, it's remarkable to me because human beings have been worrying about causal questions, like go back thousands of years, and you had primitive tribes, and should you go hunting north or should you go hunting south? And they have experience for how often they catch animals going north, and they have experience how often they catch animals going south. So the idea of what to do, how experience informs decisions that you make goes back thousands and thousands of years. But the formality of how you actually draw inferences, formal inferences, is extremely recent. In fact, it's so recent that it doesn't go back thousands of years, it doesn't even go back hundreds of years, I think. I think we only had sort of a formal structure for thinking about causality in the 20th century. So I think it's a very sort of recent idea, and therefore it's kind of remarkable that it's that recent, even though informally human beings have been worrying about causality and causal inference for thousands and thousands of tens of thousands of years. And as I developed this idea, I hope that you'll sort of agree with it. Let's see what I can do this correctly now. Wow, okay. So this is a little bit of personal history, because I think because this idea of causal inference is so important, that our ideas of how to understand it are terribly influenced by people we had admired when we were growing up. So, for example, like a lot of kids, I was went to high school in the late 1950s, and like a lot of kids, I like math, because math is sort of easy to grade. So a lot of people who are relatively intelligent sort of get good grades in math. And but I primarily like physics. I like the idea of real science, which is understanding what the real world is like. And when I went to college, I entered Princeton, and there was a program in physics. And the guy who ran this program was a guy named John Wheeler, relatively well-known physicist, and he's known for a few things. One thing is that he's credited with having coined the name black holes for this phenomenon of an object, a star that's so dense that even light, even photons couldn't escape. And he denied that he made up the name for that. Because he was giving talks, I think in the 1950s, where he was describing these objects. They were so dense that light couldn't escape. And somebody in the audience, a couple hundred people were attending the talk, and somebody in the audience shouted out "black hole." And Wheeler said he tried to find the guy after the talk, but the guy had already left. And he couldn't. So he never found out who actually made up the name. But because Wheeler started using it all the time, he was credited with that concept. Another thing about Wheeler that you probably Google and find out, he was the PhD advisor of Feynman, Richard Feynman. So he, and Feynman has important things to say about Wheeler. But the thing that influenced me, I guess, is as a freshman, 17 years old, the first problem that he gave in his physics class was, how far can a wild goose fly? And he didn't want the details, but he said, tell me the principles that you're going to use to figure out the answer. And then tell me why you think the answer that you came up with may be sensible. So how's a wild goose stay up? It's flying. Gravity's pulling them down. What's a wild goose doing? It's converting fat that's stored on the body to convert that potential energy into kinetic energy to stay afloat, and gravity's pulling it down. So the fact is, you have to figure out, how much does a wild goose weigh? Does it weigh 100 pounds? No, that makes no sense. So you had to go through these steps, just the logical steps, what you have to think about in order to approximate how far a wild goose can fly. Can it fly all the way around, the Earth, 25,000 miles? No, that makes no sense. Can it fly a couple thousand miles? Yeah, that's what they sort of do, I guess. They go from up north to down south to feed and so forth. So it was the importance of the idea of understanding basic concepts and being able to use those basic concepts to do approximations, and then to do casual calculations to see whether those approximations are realistic in terms of how. And I think that's a fundamentally important idea. And the other thing about Wheeler is an extremely modest guy. Now, at the time, if you looked at the physics department at Princeton, it had some pretty impressive people. So, for example, if you Google Wheeler, at least when I did recently, you find a picture of him, walking on Princeton campus with a well-known guy, Einstein. So that was a fairly impressive guy. Another guy who was running around Princeton at the time was a fair mathematician, von Neumann. So these were his colleagues in some sense in the math department and in the physics department. And it's hard to be arrogant when your colleagues are Einstein and von Neumann, von Neumann, arguably the greatest mathematician of the 20th century, and Einstein was, one of the most creative scientists of the 20th century, maybe the last 1,000 years. So Wheeler was a very influential guy for me, because the idea, because when you in physics and math, you tend to try to be arrogant, and if he's not arrogant, you come on, stop it, just be a normal person. But another, but the idea of this relates to causality, because in order to understand causality, you intervene, you do something, and you see what happens to the world, how it changes. When I was at Princeton, I eventually switched to psychology, and I went to graduate school in psychology. But as an undergraduate, I met another very influential guy, fascinating person, psychologist named Julian Jaynes. And he wrote a book, and when I knew him, he was writing this book. We used to have long conversations about it. And the book was entitled "The Origin of Consciousness and the Breakdown of the Bicameral Mind." And so at that time, they were doing lots of studies. Psychologists were doing lots of studies about how the brain has houses, two hemispheres. And they're only connected by a ganglia of nerves at the base of the spine called the corpus callosum. And so Julian James had this theory that the history of human beings is that for the consciousness, as he defined it, is extremely recent. So in fact, human beings were writing, publishing, in some sense scrolling, communicating before they were conscious. And what consciousness is, according to Julian, is communication between the two hemispheres going through the corpus callosum. And in thousands of years ago, we interpreted these messages between the two hemispheres that were communicated by language as voices of gods. And so the idea that people, if you look at religions, there's a lot of commonality between different religions because they interpreted these voices being zapped back and forth between the two hemispheres as voices of gods. So Julian had this theory about this. We had wonderful conversations with the guy. Was really a real scholar, and so he read all sorts of. What's one of the examples? If you look at the Old Testament versus the New Testament, he, for example, claimed that the Old Testament was written by pre-conscious people, and the New Testament was written by conscious people. And an example of that is that if you sort of study in original language, the Old Testament, people would say, last night, after I went to sleep, God came down and sat next to me in bed, and he told me to do certain things. Certainly, if you look at Greek myths, it's where, Zeus or something came to you, told you to do something. In the New Testament, I had a dream last night. And in the dream, God came to me and told me to do something. So there's a different interpretation between pre-conscious people and conscious people. And they existed side by side for thousands of years. And in fact, people now who we consider schizophrenic are really pre-conscious. It's a throwback to an older brain. Anyway, that was also, this kind of thinking was influential with me because I think it's relevant because in current study, we'll get this at the end of the talk in half hour or something, that placebo effects are very much related to this. Because everything we know, even formal mathematics, is filtered through our brain. I mean, there's no way to think about it otherwise. Everything we know or discussions, and so it goes through the brain that we talk. So Julian was very influential in my thinking about things, including causal effects and placebo effects. So this influence goes back for a zillion years, for me back to the 1960s. And then I went to graduate school, and I started out in something, some psychology, and then I changed to applied math program, computer science, and other stuff. But then I eventually changed to statistics. And of course, this history for me was a little strange, but it was influenced by the need to stay in graduate school because of Vietnam. Who wants to go trudging through rice fields in South Asia? So I had to stay in graduate school. So I switched to statistics. And in statistics, I took this wonderful course that Bill Cochran taught in 1968 on experimental design. And how do you learn about things formally? Well, you do experiments, you have randomization tests, and sort of all that good stuff that was so remarkably recent, meaning in the history of science, these ideas of doing randomized experiments was extremely recent. So that, but one thing that was clear from my days studying physics to the psychology to statistics in Cochrane, there's a clear separation between science, which is what you're trying to learn about. So science exists, it's out there, and then we do something to learn about it. So there's a clear separation between the world as it exists and what we do to learn about it. And how do we learn about it? Well, we intervene in some way, and we measure aspects at a point in time that's after what we want to learn about. So the world exists now, we do something, and we try to learn about what it was back then when we first started the intervention. And one very important aspect of this perspective is that there's the same notation, representation of science, no matter how we try to learn about it. So our trying to learn about it doesn't change what the science was before we tried to learn about it. Now, the intervention trying to learn about it often does so change the future, but it can't change the past. I'm not saying that that's necessarily true, but it's to me, it was just part of what I believe. That's what that's why I was trained. Science exists at some point in time. You intervene, try to learn about it. The learning may change it because you have to intervene. So to see things, you bombard them with photons, so that may change it, but it doesn't change what it was before. So the idea is time marches on. And therefore, any problem of inference about what the world is, it's a missing data problem. You always have missing data because the world now is not the same as it was before. Yet that's what you try to learn about what the world was at a particular point in time. See, and you can't go back in time. That's just I'm not saying it's true. You know, maybe we can't go back to the future. You know, as current fun movies suggest. So, and this is related to this Heisenberg uncertainty principle and the observer effect. Two different things, but fundamentally, the Heisenberg uncertainty, you can't measure both what momentum and position at the same point in time. There's always some uncertainty if you measure one about the other one. And the other thing is an observer effect, which says the act of observation changes the world in some way. I'm not doing this right, okay? Let's see. What am I doing incorrect? Well, let me see if I can do this. That doesn't work either, okay? What have I done?
Maybe try now with the
Okay.
pointer.
Okay, good, thanks. So as I said earlier, I think the history of really understanding what causal inference means is very recent. And I attribute one of the first essential ideas to Fisher in 1925 in his statistical methods for research workers. Because I think that to understand causality, you really have to have an appreciation and understanding for doing experiments or how you find out what is really going on. And so, Fisher in Statistical Methods for Research Workers in 1925, if you look at that book, the last chapter of the book, I think it's the 8th chapter, the last one, is on randomized experiments. So Fisher introduced randomized experiments, not in 1935 design of experiments, but in 1925. And he proposed several, I think, essential ideas. One thing is by randomizing, you actually create balance on all pre-treatment covariates. So there's a lot of mathematical work done. Probability theory was well developed, primarily through people studying gambling, games of chance. But Fisher actually proposed in 1925 that you should randomize units to different treatments. If you want to learn about the effect of one treatment versus the other, you should actually toss coins. And he actually, if you go back, there was discussion of what you should do theoretically about randomizing. Again, because people understood gambling. But Fisher said this is the way you should actually do experimentation. You should actually randomize. And I've looked and I can't find any other suggestion that says you should actually do this. It may seem like a subtle difference, but to me it's not. You know, understand the mathematics, but the mathematics is telling you to do something. And Fisher I think was the first to recognize this. Although I'm not sure he thought it was such a big deal, but as far as I can tell, and basically that's a formalization of Popperian, you know, Karl Popper, philosopher. The world advances by making up myths and rejecting the myths. You make up a story, you know the story's wrong, and science advances by showing that that story can't explain what you actually observed. Then you discard that theory and make up a new theory. And now science advances by discarding theories that are wrong. And Popper is also a 20th century philosopher. Formalize this, that this is the way science advances. Now, some recondite advice, so hidden advice from Fisher, and this is not, and I've tried to find out whether you ever wrote this down. So this is some hearsay from Cochrane. My advisor Cochrane actually knew Fisher very well because he worked at Rothamsted. So he was a relatively young man when he knew Fisher. And I asked Cochrane a question: what if you got a bad randomization, a bad allocation? You randomized, but you know all the males got treated and all the females got controlled. It is possible. So, if you look at what Fisher wrote, you should live with that randomization. But what did Fisher really say? No. You should re-randomize. You should do another random draw that had more balance. Now, so why did Fisher write something different than what he thought? Well, I think people do that all the time. You have an idea, it's your idea, you want to promulgate the idea, you want other people to use it. You don't talk about all the problems with it. You don't talk about all the details. You just, advertise, this is what you should do. Would I do that? Nah. I re-randomize. I get rid of the bad randomization because I don't want a bad answer. But the problem is the theory doesn't work. All the symmetry arguments are based on ellipsoidally symmetric distributions, which converge to normal, and you get all these symmetry arguments fall apart if you throw away bad randomizations. But in fact, that's what you should do. And even Fisher said that. And in fact, the theory and application can finally be pursued because the mathematics was never in the way, but the consequences of the mathematics were. Because the resulting distributions, even asymptotically, are mixtures of normals and truncated normals, even asymptotically. So it's sort of ugly stuff to work with. But in fact, that's no problem anymore with the computing because you can do everything by simulation, which is what you should do. And in fact, the theory and application of these ideas finally being pursued because the computing is possible. Another insight from Fisher, to assess the science, this is where the Popperian ideas come in, you hypothetically re-randomize. So you put a null distribution. And so under this null distribution, you know everything that's going on. You know the theory's wrong, because all theories are wrong. But you say, is the theory good enough to explain what I've seen? And so you put down the theory, and under this theory, in the simplest case, all the values you would have observed in this experiment, whether all the units got assigned treatment or all the units got assigned control, no matter what the randomization is, you know what you would have observed. So because of that, and because of the randomization, there's a distribution that's generated over all possible things you would have observed. And then you compare this distribution to what you did observe. And if what you did observe is highly unusual under the hypothesis, typically called the null hypothesis, then you say, I don't believe my theory. It's a sort of a stochastic proof by contradiction. The mathematical idea of proof by contradiction, you assume something like the square root of 2 is rational, you assume that, then you find, oops, I got a contradiction. So then I don't believe it. So this, the Fisherian test is a stochastic proof by contradiction. You can't prove it's wrong, but it's highly unlikely that the theory that you started with is correct, because it's contradicted by what you observe. And this hypothetical re-randomization, it led to all of Fisher's stuff, which never quite came together, but fiducial inference, fiducial distributions. But there's a critical idea there, which I think is obviously correct. Meaning you don't live with something that's contradicted by data. So and that's what the but Fisher did all this under this null distribution, typically where there is no causal effect at all. Did he ever consider non-null distributions? He really didn't. But he obviously had that in mind, because here's a quote from 1918, where he said, if we say this boy has grown tall because he has been well fed, we are not merely tracing out the cause and effect in the individual instance, in this particular case. We are suggesting that he might quite he was a terrible writer, he really was. He might quite probably have been worse fed, and in that case, he would have been shorter. So he's implicitly comparing the kid's height, having been well fed as he was, with what it would have been had he been poorly fed. So he's implicitly comparing the outcome under one treatment with the outcome under the opposite treatment, well-fed versus poorly fed. But surprisingly, he had no explicit notation for formalizing non-null causal effects. Despite these tremendous geometric insights, F distributions, T distributions, based on symmetry arguments and sort of large sample arguments. So who made up the notation? Jerzy Neyman. Neyman and Fisher in the 1930s and 40s became relatively bitter enemies. It's like very different personalities. And so Neyman, in his thesis written in Polish in 1923, defined non-null causal effects in terms of potential outcomes. So potential outcomes are these things that you would observe under one treatment and comparing them to what they observed under the other treatment. So he defined estimands, quantities to be estimated. And in this thesis, his master's thesis, in randomized experiments as functions of potential outcomes for these n units. Let's suppose there are n people in the study. And so y0, the outcome y, are the vector of potential outcomes. If everybody got assigned a control treatment, y1, for example, is the array of potential outcomes. If everybody got assigned the active treatment, and you assume something that I called Sutton's stable unit treatment value assumption, which is basically just an assumption that says this notation where you have y, I, j, person I, treatment j, is well-defined. So it's well-defined in some sample space. Sample space could be reals, it could be complex, or it could be functions. It doesn't make any difference. So the stable unit treatment value assumption says this: yi for unit I, treatment w is a function of just I and w. And he explicitly mentioned in this 1923 thesis that the problem of inference for causal effects is you can't observe both of them. So it's a missing data problem. So causal inference explicitly he recognized is it's a missing data problem. And this of course, to me, was a completely natural way of thinking about things. Because, you know, as a kid growing up with physics even in the, when I took it in the 50s, you know, the idea of quantum mechanics and, you know, unobservable things, it's, you know, and Heisenberg, and it's all acceptable. So it's an acceptable way of thinking about things. And I'm not saying that I understood then or even understand now the physical principles, but the idea is just you can have things that are well defined, but are defined in terms of quantities, both of which you can't measure. It was, and Neyman understood the role of non-additive unit level causal effects. So what does non-additive mean? Well, if I give you the active treatment, it adds 5 years of life. 5 years of life for everybody? Yeah, that's what additive means. It's an additive effect. Same constant effect for everybody. And Neyman in 1923 realized that this possibility of non-additivity changes inference. Doing inference for a causal effect depends on whether effects are additive or not, whether they're constant across all units. But in an interview, I think in 1960 something, he denied the depth of understanding that he had in 1923. Basically, he said, I was just screwing around with algebra back then. And like a lot of math, I really didn't know what the deep ideas were. But I thought that the formulation of causal effects in terms of these potential outcomes was good. So the mathematics was trivial. So there's all these, you know, unbiased estimation and confidence intervals. That was screwing around. But the basic notation was an important advance. And that's it's interesting to me because it shows how people can do something and do something that's formally correct, but say I really didn't know what I was doing. I really didn't know what was important. Some comments on these insights. I sort of said this earlier, but I think these are 20th century insights like those in quantum mechanics. Actually. So the early 20th century, you know, because quantum mechanics basically in Copenhagen schools, early 20th century, 1910. The 20th century, like the insights in quantum mechanics. So estimands, quantities you want to estimate, the things that are important, causal effects, are defined in terms of measurable quantities, which are not simultaneously measurable, even theoretically. Position, momentum, you can't measure them both. But you can measure either one you want precisely. So one thing that's interesting to me was Fisher really the first to propose causal effects are defined this way. I've looked, and the closest thing that I can come to is an American psychologist, philosopher, Peirce. That's a strange way to spell the name Peirce, but that's the way it's pronounced. And his father was a Harvard mathematician in the 1850s or something like that, late 19th century. But so what he did is he used randomization in the context of an experiment. But he didn't use randomization for inference. He used randomization in a psychophysical experiment to try to assess whether your assessment of the weight of this is affected by the previous weight I picked up. So we have light weights and heavier weights, and he randomized the order of presentation so that the person couldn't anticipate what the next weight would be. So Peirce actually explicitly recommended the use of randomization in an experiment, but it had nothing to do with the inference. So the inference was not based on the randomization distribution. So as far as I can tell, Fisher really was the first person to use the randomization as the basis for inference, which is kind of curious because randomization was being used for other things. In games of chance, everybody used randomization. You know, the black is equally likely as red, and you have to take away the 0 and double 0 in order to know the odds. And shuffling decks, everybody knew about that for 1,000 years. But Fisher was, as far as I can tell, was the first person to do this little step to say the randomization should be used as the basis for inference. I think he really was the first. And because of this, randomized trials, after Fisher proposed them in 1925, quickly dominated agricultural, animal breeding, and in fact, that's what led Fisher to write Design of Experiments, DOE, in 1935. And he expanded chapter 8 in the book and got rid of chapter 8 in the subsequent editions of statistical methods for research workers. And I think that's why lots of people misrepresent when randomization was proposed. Because if you look at the later editions of statistical methods for research workers, for example, the last edition was published after he was dead and living in Australia. Chapter 8's no longer there. But if you look at the earlier editions, the discussion of randomized experiments does appear. And I think that's important. And because of that, he decided, if you look at the preface for Design of Experiments, for the preface for the first edition, it talks about how the concept of Design of Experiments has become too important to just be one chapter in a book. So I'm going to write a book. And that's why I wrote Design of Experiments. And after Design of Experiments, randomized experiments became really commonplace in agricultural, animal breeding, throughout the Commonwealth, the British Empire, Australia, and the United States. And a lot of applied work was done by followers of Fisher, like Oscar Kempthorne, Cochrane, and Cox. That's Griffith Cox, not David. George Box, David Cox, 1958, Planning Experiments. Some great books. And if some of you haven't looked at the original books from that era, they're really beautifully clear because they really knew what they were doing, and they really did experiments. Cox 58 is still a great book. And of course, there was supporting mathematical work done outside of the Commonwealth. For example, in Indian Statistics Institute by guys like Mahalanobis, R.C. Bose, Nair, C.R. Rao. C.R. Rao is still alive at like 100.5 or something like that, because he had his 100th birthday about 6 months ago. And subsequently, randomized trials really entered Western industry because cars, manufacturing became so complicated. There's so many different things to vary. You had to do experiments to figure out what's going on. You couldn't just make up stories. And of course, ideas like fractional replication, where you're varying 10 factors at a time, became very important. But these insights were limited to randomized controlled trials with non-conscious units, meaning like plants, animals, and maybe some animals are conscious. That's a different issue. If you're doing experiments with paramecia, probably they're unconscious. But human beings are conscious. Well, how about octopus? I mean, octopus are pretty smart, and dogs are pretty smart too. So maybe they do have some consciousness. And why is that relevant? Well, it's relevant to the whole idea of double-blind controlled trials. And so the transportation of these insights to randomized trials with conscious units is relatively more recent. The first example I can find, I'm not saying this is right, but I looked a little bit, was in England in 46. Medical Research Council and Sir Bradford Hill, where they're studying the effects of antibiotic treatment on streptococcus. And then the big trial done in the US was salt vaccine, which was done in 1954. A randomized trial involving thousands of people. They did salt vaccine really prevent polio. And this led to actually incorporation in the US Food and Drug Administration and approval of pharmaceutical products. And there was a guy who's very influential in this, a US statistician, named Paul Meyer, who wrote about this stuff in the 1950s. And really, from his perspective, you have to do randomized experiments if you're going to learn about causality. It really works. It's sort of surprising, but before 1950, drugs were approved by a committee of doctors who actually use the drugs. And the doctors would argue, oh, this works. Well, I had a patient and she was young and it worked. And I had a patient and she was old and it worked. So therefore we should do it. And just discussion like that, they can do experiments. It's all based on observational studies, as sophisticated as they got. And the way these data were analyzed is by regression. So there was no use of these Fisher name and insights or the notation in non-randomized trials. So on one hand, the notation and the insights in randomized experiments were clear. But when they went to observational studies, everybody did regression. So a great example of that is the 1964 Surgeon General's report on the effect of cigarette smoking on lung cancer. No randomized experiments. And in fact, there never has been a randomized experiment, even with animals, that shows cigarette smoking causes lung cancer. It's all based on observational studies, not randomized. And you know what? So why can't we do randomized experiments? Well, on rats or pigs or something, they don't live long. So cigarette smoke gives them skin cancers. But when do people typically in the US start smoking when they're mid-teenagers, maybe 16, 17? They get lung cancer when? 50, when they're 50, 60 years old. It takes half a century to develop lung cancer. You know, show me a 50 or 60-year-old dog or a 50 or 60-year-old rat. I mean, but so all the evidence on smoking and lung cancer is observational. But I imagine most of you believe that smoking is not a health food. You know, it causes lung, but all that evidence is based on observational studies. And these studies, if you look at them, they're all based on regression. So they're not using any of the insights, the Fisher name and insights from randomized experiments to do the analysis. Epidemiology, economics, social science, they all used regression with the potential outcomes, this idea of Y1 and Y0, only one of which you can observe and the unit is lost. So the potential outcomes, the pair of potential outcomes, is replaced by the observed value. So the Y odds in this notation is the indicator for treatment versus control times the observed potential outcome if you're treated, plus 1 minus the indicator. So the indicator is 1 if you're control, times the observed potential outcome if you're exposed to control. And this violates the principle that I started out talking about of the clear separation between the science from what we do to learn about the science. Should I be ending, I guess, right? Okay, I will stop. I think I can probably end with one more. So there's this thing that Paul Holland called the Rubin causal model for a series of articles that I wrote in the 1970s. Which were actually, this is to encourage younger folks. All of these articles were originally rejected, soundly, because they were just wrong. You know, they're either wrong or everybody knows it. So, but eventually they got published. And the key ideas here with potential outcomes, its use of potential outcomes defines causal estimates in all situations, not just in randomized experiments. And Neyman actually disagreed with me about this, because I visited Berkeley in the mid-1970s, and I had an office next to his, because visitors and retired faculty had offices on the same floor of Evans Hall. And he said it was too speculative to talk about causality outside of randomized experiments. You should only talk about causality in the context of randomized experiments, observational studies. You shouldn't talk about causal effects. And one of the contributions of these papers was they had an explicit representation for what I call the assignment mechanism, for the probability of being, what the assignment mechanism was. And one of the big advantages of randomized experiments is the assignment mechanism doesn't depend upon the potential outcomes. So this expression, I guess you can use it well, so that the probability of treatment assignment given covariance X and the potential outcomes is free of the potential outcomes. That's, I call it unconfounded in this other definition of ignorable. And Bayesian modeling for experiments models the sign. So it puts a model on the thing that you're conditioning on to do the treatment assignments. And it creates missing and observed potential outcomes. Say, an artistic touch is needed here. These all models are wrong. And that expression goes back to George Box and many people before that. And I say an artistic touch is needed because the model is wrong. So you know that you're putting down something that's wrong. It's not true. And that's why an artistic touch is needed. In fact, there's an interesting quote from Picasso when he was asked to comment on computers. His comment is, computers are worthless. They only give answers. And I think that's actually a lot deeper than it might first appear, because the most of science advances by asking questions. And the formulation of the question, it's hard to get a computer to formulate a question. And so, okay, like you give a computer a problem and it's unsolvable, that there's no answer. What does it do? So it gives up. But what do people do? They modify the question into a question that does have an answer. And the question is sort of like the original one, but it does have an answer. So I think this is where the Picasso quote is relevant. Something that only gives an answer to a precise question is often not a good question, not an interesting question. So the fundamental problem facing causal inference is a line I made up, and it's a missing data problem. So here you have a bunch of units, 1 through n, and there's a column for the outcomes under the active treatment, y1. There's a column for the outcomes under the control treatment, y0. And then there's an indicator for which treatment you've got. And so the checks refer to things that are observed, and the question marks refer to things that are missing. And so the random assignment of active versus control means a representative sample of y1 will be compared to a representative sample of y0. It's sort of obvious. I mean, once you have a notation, the idea of randomization, which people knew about, again, for hundreds of years, it's sort of obvious that you want to do random assignment, because you get a representative sample of the y1 outcomes, and you get a representative sample of y0 outcomes. Well, if it's so obvious, why did it take thousands of years to come up with that? Well, I think what you have to do is combine two things. One, Neyman's notation for the potential outcomes, and Fisher's insight into doing randomization. Because once you have the combination, this little matrix is trivial. But then why did it not become the basis for all causal inference, whether it's a randomized experiment or an observation study? I have no idea, because it seems obvious to me. In fact, when I wrote this 1974 paper, it was 75 paper, I did it not because I thought it was new, just because I wanted to formalize something, like notation for. But the critical thing of writing it this way is you have to model the assignment mechanism to draw inferences about the missing potential outcome. You have to have a model for how you assign treatment. It's a model on W, given background variables, and then if you're going to do Bayesian, you have to have a model on potential outcomes. And it's a mistake to regress the observed value. Okay, I have to finish in 1 minute, because this is the second to last slide. So using this regressing the observed value on these indicators is bad. It loses the missing data aspects of it. It mixes the assignment mechanism and the science. It suppressed these key insights from Fisher and Neyman. But it became standard in biostatistics, economics, everywhere, and even great statisticians and epidemiologists. So Fisher, Cochrane, Cornfield was the main guy who was involved in the tobacco litigation, and was the main statistician who led to the studies prohibiting tobacco smoke. And they confused themselves with this observed value notation. And it's screwed up, and it's even worse in case control studies for cases on people with the disease, the controls and people without the disease, because you're sampling based on the outcome. So automatically it's confounded. So instead of just basing it on covariance, you're basing it on the outcome variable. And this is just a quote from Cornfield. That he's just distinction between the kind of inferences that can be supported by observational studies and by randomized experiments, saying that there is a distinction is obvious, but it's hard to formalize. And the fact is, it's not really hard. Just is the assignment mechanism unconfounded? Does the assignment mechanism depend upon the potential outcomes? So starting to conclude this last slide, so I'll be done in half a minute. Retain key insights from the past. Don't go back to Neyman, Fisher, and read the original and see what the insights really are. And get rid of confusion from the past. So get rid of doing regression. And realize that randomized controlled trials are extremely recent, and update statistical methods for both design and analysis take advantage of model. Computing has a tremendous role to play, not conceptualizing, but actually doing the design and analysis. Encourage mathematical precision, especially in notation and logical flow, because the precision can have critical consequences for challenging applications. For example, in placebo effects, which comes back to the role of psychology and all this stuff. And that's it. Thanks very much. I'm sorry, I probably do not have time for questions. I got to get out of here.
So next week, we'll have another lecture in the series by Professor James Robbins. That lecture will be online on Zoom and YouTube. It'll be at 10:30 a.m. on September 10th, so make sure you join us for that. Somewhere.
Excuse me. So do you know where to sign in for students?
Yeah, student present on the table there.
And also, I just switched to this seminar this week. I was in an